So our starting point here is going to be the product rule. So for example, if we were taking the derivative of this product, and so if you're kind of curious, that symbol is mu. I'll say the textbook uses an R to denote this instead of a mu. So if I wanted to express the product of these two things, it could be y prime times mu plus y times u prime, for example. So this left side of the differential equation that we start with, we could actually write this as y plus, y prime plus 2 times y. Just kind of writing the product rule like this, you can see we have like y primes matching up and we have y's matching up. So it makes sense that this could be massaged into a product rule. And that's what we're going to try and do. We're going to introduce this thing mu. We're going to multiply both sides of this differential equation by mu. So the differential equation we started with is start above. So I'm going to write this as mu times y prime plus 2 mu times y is equal to 3 times mu. Okay, so again, we're just taking that differential equation up top and multiplying both sides by some unknown function called mu. So as long as I do that to both sides, I haven't changed the equality relationship here. In order to make this look like the product rule, we've got our y prime mu. So that part checks out. And then we've got this other term over here, which should match up with this one. So this tells me that this 2 mu should equal the derivative of something, should be the derivative of mu. So in order to put this into the product rule, we must find some solution to this differential equation. We want to find the function mu so that its derivative is equal to 2 times itself. And this mu is going to be what we call the integrating factor. So we'll see why. It's going to be a factor that's going to allow us to integrate the left side of the differential equation. So here we can separate this differential equation, right, by thinking about mu prime as d mu dx. I bring the 1 over mu to the left side, and then I bring the dx to the right side. And let me just say here, we don't need to describe every single mu that's going to work. We just need to find one such mu that's going to work. So at this point, I ignored a constant of integration. And we'll include the constant of integration at the very end. So I'll just say at this stage, we can ignore the plus c, since we just need to find one such function, as opposed to like describing all such mu. If I exponentiate both sides of that previous line, then what we'll get is one such function is going to be mu is equal to e to the 2x. So we did this box already, right? So this is saying solve that differential equation above, which we found to be e to the 2x. And so let's plug this back into the differential equation that we had up here at this stage. So we had, we wanted to find mu. Okay, so the whole point was we wanted to find the function mu that's going to make the left side look like something that was a product rule. And so I can now plug in that we have e to the 2x, and then my mu prime would be 2e to the 2x by is equal to 3e to the 2x. So all I'm doing now is plugging in the expression for mu that we found in the previous step. And now you can see that the left side of this differential equation we have now made it into something that comes directly out of a product rule. That whole left side now looks like e to the 2x times y derivative. If I took the derivative of this thing, you can check that you would exactly get back the left side in the previous step. So at this stage, we multiplied basically both sides of the differential equation that we started with by e to the 2x. And that gives us a new differential equation. And now we can integrate both sides of this differential equation with respect to x. And this is an okay operation because, again, we're doing the same thing to both sides. Both sides we're integrating with respect to x. So integrating the right side, not too bad. Then on the left side, remember the derivative and the integral, they undo each other. So what we get is e to the 2x times y. And that just about does it, right? And so the last step that we typically do is divide both sides by e to the 2x to solve for y. And so here, be careful, we can't just say that dividing c by e to the 2x just gives me some other arbitrary constant, because what we're dividing by depends on x, right? And so we want to keep that dependence there. So we're taking some arbitrary constant and dividing it by e to the 2x.
Does the e to the 2x y like derivative, is that with respect to dy dx or with respect to y? Because
So,
the dy, it cancels out when we just take it with
yeah, this prime is a derivative with respect to x. So that when we integrate that with respect to x, that's why they undo each other.
That makes sense. Thank you.
Just to finish this one up, we would probably want to write this a little bit nicer as something like y is equal to, well, those two e to the 2x's cancel out. So we have actually just 3/2 plus c e. We can just write dividing by e to the 2x as e to the minus 2x. And this would be our general solution to the differential equation that we started with. So the whole key to this process is exactly described right here. It's finding this factor mu that when we multiply the differential equation by mu, it's going to make the left side into a derivative. That comes out of a product rule.